Okay, hello everyone, let's go ahead and start and let's take a look at infinite series. Now again, remember what we're trying to do is we're trying to determine whether or not an infinite series now is going to be convergent or divergent. Now let's go ahead and first of all define what we're talking about with regards to an infinite series. And remember, we did this a little bit with the infinite geometric series. We just basically said that if this is going to be the series or the sum of all of the terms of a particular sequence, then it's going to be all of the terms added together up to the infinite term. So in other words, we just keep on adding those terms, an infinite amount of terms. And therefore what we're coming out with is a representation of an infinite series that looks like the summation from I is equal to 1 to infinity of a sub I. Now what we're also going to have to be concerned about as well is what is called the nth partial sum. Okay, what we're going to do is we're going to say that if we go ahead and take a look at any of the first n terms, in other words, the summation from I is equal to 1 to n of a sub I, we're going to call this the nth partial sum of that particular infinite series. Okay, so let's go ahead and take a look at a couple of facts here. We know that if we take the limit as n approaches infinity of s sub n, which is basically this here, and it is equal to s, which is going to be any number, and this number exists, we say that the infinite series converges to that number s. Otherwise, it is going to diverge, and it's going to diverge to either positive or negative infinity. Okay, here's a theorem that we want to go ahead and use. It's going to say that, well, if we know that a particular infinite series is convergent, then we know that the limit as I approaches infinity of the sequence generator has to go to 0. Now, what that means, just in a very conceptual sense, is that if I keep on adding all of these terms and an infinite amount of these terms, in order for me to actually come up with a value of s, these values had better get closer and closer and closer and closer to 0. So that's what we mean here by saying that the infinite series is convergent, means that the sequence has to converge to 0. Now, the thing that we have to be careful of is we cannot assume that the converse is true, because it is not. If the limit as I approaches infinity of a sub I is equal to 0, then the infinite series is convergent. And remember, we said that that is not going to be the case because of the fact that we have a sequence 1 over I, that even though it converges, the sequence converges to 0, the infinite series is actually going to diverge. So be careful about this one. This of course is true, but this is not true. Now again, being that we're dealing with convergent or divergent, well, one of the things that we can do very quickly is determine whether or not a particular series infinite series is going to diverge. Okay? And what we can say is we can say the contrapositive of what we said here. It says that if the limit as n approaches infinity of a sub n, if that does not go to 0, or if it goes to infinity plus or minus infinity, then of course the infinite series has to diverge. Now let's go ahead and get an idea of what that means. If we come back up here, and if I continue to add all of these values, and all of these values go to a number other than 0, then that means that the infinite series is always going to be increasing or decreasing depending upon the values of the actual terms of the series. So, very quickly then, if we can show that the sequence generator is actually the limit as n approaches infinity of the sequence generator does not go to 0 or it goes to any number, then what we know is that the infinite series will then diverge. Now, the other one that we can use in order to determine whether an infinite series converges or diverges is we can use the comparison test, which we've already experienced before, just in a different form. We said that let a sub n, a sequence a sub n, be a positive sequence. Therefore, if the infinite series b sub n converges, and we know that all of the values of a sub in the sequence a sub n is less than or equal to the values of the sequence of b sub n, then we know that the infinite series a sub n will converge. So this is the concept again. is basically what we have is we are comparing all the sequence terms, and then if we go ahead and add them all up to an infinite number of terms, then I know that since this one here is going to converge, then I know that this one here also has to converge. Okay, in the same respect, we said that if the infinite series of b sub n diverges, and we know that b sub n, sequence terms, are always going to be less than the sequence terms of a sub n, then we know that the infinite series a sub n will also diverge. So the concept again is that if I have 0 is less than b sub n, which is less than a sub n, so again what we're doing is we're comparing the sequence terms, then if I go ahead and add all of them up, and I know already that this one is going to diverge, then that one has to diverge as well. Okay, so just to wrap things up again, we wanted to go ahead and make sure that we knew the definition of an infinite series, also know what the nth partial series, partial sum of the infinite series looks like as well. And some key facts, again, is we said that if we know that the infinite series is equal to a particular value of s, then we know that the infinite series converges, otherwise it diverges. And we can very simply go ahead and test for divergence based upon this theorem here, or we can use the comparison test to, again, determine whether an infinite series converges or diverges. Okay, so we'll go ahead and take a look at a couple of examples in class the next time that we meet. See you later. Bye-bye.